Fermat's little theorem works when the modulus is prime. Now we look at a more general theorem that works for many composite moduli as well. And so this is going to be called Euler's theorem. And it says the following. If a and n are integers, and the greatest common divisor between them is 1, which means they are coprime, so if a and n are coprime, then there's this function that we'll talk about such that a to the power of phi n is congruent to 1 mod n. And so this function is called Euler's totient function. And what Euler's totient function does is it counts the amount of integers between 1 and n. Here you don't include n, so let's say between 1 and strictly smaller than n. So it's going to be between less or equal than 1, but strictly smaller than n. So how many of these numbers are relatively prime with n? That's what this phi of n does. So in particular, if p is prime, then phi of p, so if you look at the numbers between 1 and p, there's going to be p minus 1 of them, and all of them are relatively prime with p, so this is just going to be p minus 1. And so that means that if you take n prime here, this is just going to be Fermat's little theorem. And so this is a generalization of Fermat's little theorem. So let's look at an example here. So let's consider, for example, the number 9. So you have the numbers 1. So let's list them all out. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many, without the 9, just until 8. So how many of these are coprime with 9? So 1 is coprime with 9, 2 is coprime with 9, 3 divides 9, so it's not coprime with 9, 4 is coprime with 9, 5 is coprime with 9, 6 is not because they share 3, right? 3 divides 6 and 3 divides 9, so this is not. 7, since it's prime, it's coprime with 9. 8 is coprime with 9. So there are 6 numbers that are coprime with 9, so this means 6 numbers are coprime with 9. So 6 numbers between 1 and 9 here are coprime with 9. And so this means that the Euler totient function of 9 is equal to 6. And then by Euler's theorem, what this means is 2 to the power of 6, for example, is going to be congruent to 1 mod 9. Right? So since 2 and 9 are coprime, 2 and phi of 9 is 6, that means 2 to the power of 6 is congruent to 1 mod 9. So if you do 2 to the power of 6, so 2 times 2 is 4, right? Times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So 64, if you divide that by 9, it's going to be, so 9 times 7 is 63 plus 1, 64, right? So indeed, this will be 64 is congruent to 1 mod 9. Also, for example, if you compute what is phi of 10, you'll see that it's equal to 4, and this means that, for example, 3 to the 4 is congruent to 1 mod 10. And so this gives us a generalized version of Fermat's little theorem, where we can now not only use prime numbers here, but also use composite numbers, right? Now, how do you compute this function here? So of course you can list it out and count, but you can also show that if you know how to factor the number, so if you can factor n in this way, you can write it like this, right? So for example, we saw that so 9 is going to be equal to just 3 squared. And so this means that phi of 9 is equal to 9 times 1. So 9 times 1 minus 1 over 3. So it only has, essentially, this depends only on the amount of, on these primes that you have in your factoring. The powers actually pop up inside of this n here, but they're not relevant to the formula here. So let's compute this. So 1 minus a third is 2/3. So this is 9 times 2/3. And so 9 divided by 3 is 3. So 3 times 2, which is equal to 6, which is exactly what we had found over here. So this gives you a nice little way of computing this. Let's say, for example, take the number 1000. So if you factor this, this will be 2 cubed times 5 cubed. And so what this implies is the phi to the 1000. So the totient function of 1000 is going to be equal to 1000 times 1 minus half times 1 minus 1/5. And so this will be 1000 times half times 4 over 5, which will be equal to 400. And let's see an example that actually will use this here. So let's say that you want to find what are the last 3 digits. So of course, when you write this in base 10, what are the last 3 digits of 7 to the power of 803, right? So that's a huge number. And of course, one could try to compute it and look at the last 3 digits. But we're going to show how we can use Euler's theorem to compute this much more efficiently. Now notice that to find, so let's write it here. So to find the last 3 digits, that's the same actually as computing 7,803 mod 1000, right? So if you divide, because if you divide by 1000 and you take the remainder, that's what's going to be your last 3 digits, your last 3 digits of that number. So essentially what we want is to find what is the remainder of 7,803 modulo 1000. So let's use Euler's theorem. So first we need to check that we can. So first note that if we do the GCD of 7 and 1000, this is equal to 1 because 7 is prime and it doesn't divide 1000, right? And so that means that we can apply Euler's theorem, and so we just need to compute phi of 1000 here. And so we already did phi of 1000. So we saw that phi of 1000 is equal to 400. So phi of 1000 is equal to 400. And with this, we can show, so by Euler's theorem, so by Euler's theorem, 7 to the power of 400, which is phi of 1000, is congruent to 1 mod 1000. And now we can use this to find what we want. So 7 to the 803, if you divide it by 400, this is going to be 400 times 2, right, for the 800, plus 3. And you can rewrite this as 7 to the 400 squared times 7 cubed. And so we just saw that 7 to the power of 400 is congruent to 1 mod 1000. So this is just going to be 1 squared times 7 cubed. And so it's just going to be 7 cubed. And so if we do 7 times 7 is 49, times 7 is 343 mod 1000, which means that the last three digits of this huge number, 7 to the power of 803, is going to be 343. And you can actually compute all of this here. You can just compute it by hand. So you can really find the last three digits of this just by hand using Euler's theorem.